Great.
Okay, go.
Okay, it's a great pleasure to introduce today's speaker, Emily Nardoni. Emily was an undergrad at MIT and did her PhD advised by me at UCSD. And now she's in her third year as a postdoc at UCLA. Emily has a great new paper together with Anish Manohar on applying effective field theory methods to compute RG improved effective potentials. But today, Emily will talk about something completely different, her interesting upcoming work. So without further ado, let's welcome Emily.
Thank you very much. Thank you for the opportunity to speak here. So today I'd like to tell you about some work that I've been doing with my collaborators at UCLA, Eric Doker, Thomas Dimitrescu, and Efrat Gershkovitz. So I'd like to tell you what we can learn about SUN adjoint QCD from Seiberg-Witten theory. So an old and interesting problem is how to probe the low energy structure of gauge theories at strong coupling. This is especially difficult in non-supersymmetric cases where I have less tools at my disposal. So today I'm going to be interested in trying to make progress on this question in the context of adjoint QCD. So by adjoint QCD, I mean the 4D gauge theories with SUN gauge group and NF massless Weyl fermions in the adjoint of the gauge group. So these theories are asymptotically free for NF less than or equal to 5. And the low energy structure, the low energy behavior of these theories is relatively pretty well understood for the low NF cases. So I'd like to briefly review what we know about those cases. So NF equals 0 is pure Yang-Mills theory, and it depends on the theta angle and is expected to confine for all theta. NF equals 1 is supersymmetric. It's n equals 1 super Yang-Mills. The NF equals 1 is the gaugino, and these n equals 1 super Yang-Mills is confining and gapped. There are n degenerate supersymmetric vacua that are labeled by the phase of the gaugino condensate. And so these are very well studied theories. Now, the higher NF theories are relatively less studied or less well understood. And so today I'll be focusing on the case of NF equals 2 adjoint QCD, where there's less solid evidence for how this theory behaves at low energies. So first, let me introduce some of the main properties of NF equals 2 adjoint QCD. So this theory has, of course, SUN gauge fields and the adjoint Weyl fermions. These lambdas here, I'm using I equals 1 or 2 is a doublet index. These transform in the doublet representation of a chiral SU NF equals 2 symmetry. There is an axial U1, I'll call it U1 little r symmetry, which is broken by an ABJ anomaly to a Z4n discrete subgroup. Charge conjugation and time reversal are preserved. I'll generally use C and T rather than P for the discrete symmetries. And there is a ZN1 form symmetry, which is associated with the center of the SUN gauge group. Another important feature of these theories is that for NF equals 2 is that the Vafa-Witten theorem tells you that CT and the U1 subgroup of the chiral SU NF equals 2 cannot be spontaneously broken. So like I said, we know less about we have less solid evidence for the IR structure of this theory. However, standard assumptions about how vector-like gauge theories behave suggest the following picture for what happens at low energies. So this picture is that the chiral SU NF equals 2 symmetry is broken to a U1 by the condensation of a fermion bilinear. That the Z4n, and then this fermion bilinear also breaks the Z4n to a discrete Z4 subgroup. The one form center symmetry is unbroken, and therefore this theory is confining at low energies, and the C and T discrete symmetries are unbroken. So this spontaneous symmetry breaking pattern of the chiral SU NF equals 2 to U1 gives two Goldstone bosons, which parameterize a CP1 sigma model. And so this proposed phase that I'm describing for you, I'll call it a CP1 phase. And there are n degenerate copies of the CP1. These are related by the, or these are given by the n different values of the phase of the fermion bilinear. So one good piece of evidence for the consistency of this proposed phase is that it is economical in the sense that it doesn't require phase transitions in order to be consistent with the lower NF phase structure, which I briefly reviewed for you before. So what I mean by this is if I add small fermion mass deformations, then I can match on to the expected features of the n equals 1 vacua and then the NF equals 0 pure Yang-Mills vacua. So the question I'd like to ask in this talk is, can we test this proposed CP1 phase of NF equals 2 adjoint QCD, or can we provide evidence for it? And also from here on out, I'm entirely focusing on NF equals 2. So when I say adjoint QCD, I mean NF equals 2 adjoint QCD. So the strategy that I'm going to utilize is to embed adjoint QCD into n equals 2 super Yang-Mills. And so this is following work by Cordova and Dumitrescu. The basic observation is that we can flow to SUN NF equals 2 adjoint QCD from n equals 2 super Yang-Mills by integrating out the complex vector multiplet scalar. And so when I do this, the SU NF equals 2 chiral symmetry that I described for you of adjoint QCD, this is exactly identified with the SU2R symmetry of the n equals 2 theory, and the gaugino in the in n equals 2 is are these Weyl fermions that I wrote down. So this suggests the following strategy, that we add the soft supersymmetry breaking non-holomorphic mass term that I've written here, this m squared trace phi bar phi. So the first comment is that this mass term, trace phi bar phi, it is the real scalar at the bottom of the protected n equals 2 stress tensor multiplet. So in particular, it can be tracked to the IR, it can be tracked to the Coulomb branch of the n equals 2 theory. So this is following work by these authors. Now, for m small compared to the strong coupling scale of the n equals 2 theory, m is this SUSY-breaking parameter. We can reliably analyze the effect of this deformation, and this is because we know the exact low energy effective description of the n equals 2 theory. It's a Seiberg-Witten theory. This is very, very well studied. Now, for m much greater than the strong coupling scale, we flow to adjoint QCD. So an important comment is that this deformation that I've written down, it preserves all symmetries of n equals 2 and adjoint QCD except supersymmetry. But for example, it preserves the SU2R, chiral SU2R symmetry and all other symmetries. And so therefore all anomalies are automatically matched for any value of m along this flow. And so if I do this soft SUSY-breaking procedure and I study the phase structure as a function of m, any phase that we encounter as we vary m is a candidate phase of adjoint QCD in the sense that it satisfies the consistency checks of the same symmetries and same anomalies, and the anomalies are matched. Now, of course, the m large limit is uncontrolled. So with this procedure, I can suggest phases, but I can't actually prove which phase will be realized by adjoint QCD. So the question I'd like to pose for the rest of this talk is the following. Using the softly broken n equals 2 theory, as I just described it, can we find an effective description which qualitatively reproduces the features of this likely CP1 phase of adjoint QCD? So this is the question, and this is a bit of a loaded question. There are some immediate difficulties that present themselves. So the first difficulty is that, well, I told you that we can analyze reliably at small m. And so if I do this, if I analyze this SUSY-breaking at small m, and I do so at various points on the Coulomb branch of the n equals 2 theory, the resulting phase I would get is a Coulomb phase with massless gauginos. And so this phase is very far from this CP1 phase I described for you earlier. So the comment is, if we hope to make contact with the CP1 phase, it will be at larger m, which is the uncontrolled regime. And it will require at least one phase transition from this Coulomb phase type vacuum. Okay. Then the second comment is that, well, the n equals 2 moduli space is very large, and where on this moduli space should I try to do this analysis if I'm trying to realize this goal? So the answer to this question, I'll argue for you, is the multi-monopole points, or the maximal degeneration points of Seiberg-Witten theory. So for the rest of this talk, I'll start by briefly reviewing these multi-monopole points and motivating them as a starting point for our analysis. Then I'm going to add the SUSY-breaking deformation to the effective Lagrangian near these points, and I'll describe for you the results of a semi-classical analysis of the resulting phase structure. And the result that I'd like to describe to you is that we find a sequence of phase transitions as a function of m that interpolate between the supersymmetric phase, the supersymmetric Coulomb phase at small m, and a CP1 phase with these properties I described for you, the chiral symmetry-breaking and confinement and so on, at large m. So this is where we're going. Are there any questions before I continue? Okay. So let's start with some review of the n equals 2 moduli space. So I'll remind you that n equals 2 SUN super Yang Mills has an n-1 complex dimensional moduli space of degenerate supersymmetric vacua known as the Coulomb branch. And a gauge invariant basis on this moduli space is given by the coordinates I'll call them UK. So these are traces of products of the vector multiplet scalars. At a generic point on the moduli space, the SUN gauge symmetry is broken to a U1 to the n-1, with n-1 abelian vector multiplets describing the low energy theory. And so I'll call the scalar in these abelian vector multiplets, I'll call it phi also, but it's a var phi. and I'm using this little m index to index the n-1 U1 gauge groups at low energies. So a Z4 discrete symmetry is generically preserved on the Coulomb branch. And so the symmetry that acts non-trivially on the moduli space is a Zn, which is the discrete Z4n mod Z4. So there are singularities on this moduli space where additional particles become massless. And when a monopole becomes massless, there is a hypermultiplet charge under a U1 gauge factor that describes the light monopole. And so I will call the scalar of this hypermultiplet, I'll call it H. It also has this little M index indexing the n-1 U1 groups, and it's an SU2R doublet. So it has this little I index, like the fermions. Now, there are n multi-monopole points, or maximal degeneration points, which are related by this Zn symmetry. And at each of these multi-monopole points, n-1 mutually local dions become massless at once. And so these are the points that were studied by Douglas and Schenker in the 90s. In an appropriate duality frame, one of these multi-monopole points describes n-1 light monopoles becoming massless. And so in this frame, these abelian vector multiplet scalars are identified with the A-dual periods of Seiberg-Witten theory, and will work in this frame. So with this little review out of the way, the question is, why am I going to be focusing on these multi-monopole points in particular? And an initial good motivation is simply the fact that this worked for SU2. So this goal of realizing the CP1 actually worked for n equals 2, SU2, adjoint QCD. And so let me briefly review these, or I'll review these results by Cordova and Dumitrescu. So for SU2, there are exactly 2 singular points. There are the monopole and the dion points. Here I've just drawn them on the U-plane. And so, so the first comment is, if I add this SUSY-breaking deformation at a generic point on the Coulomb branch, then the minimum of this potential is at the origin of moduli space. And so that's what I've plotted here. And then at this minimum in this vacuum, only the scalars get a mass, and the theory is in a Coulomb phase. Okay, so that's what happens at some generic point on the moduli space. Now, if I expand the potential and the SUSY-breaking deformation near the monopole point of the SU2 theory, then I get the following expression. Let me point out the main features. So first of all, this gives the deformation. Remember, it goes like m squared. M is the SUSY-breaking parameter. It gives a positive mass to the abelian vector multiplet scalar. It gives a tachyonic mass to the monopole fields, these hypermultiplet scalars. And also, it gives a tadpole, this linear in phi term, from matching to the expression on the Coulomb branch. So let me go back for a second. So what that's coming from is, when I integrate out the hypermultiplet, I'm supposed to match onto this curve I've plotted here. And in this curve, at the monopole point, I'm sitting on some slope. So this tadpole is the linear approximation of this potential at that point. That's what this is doing. So I can analyze this potential, and let me describe for you the results. So here I've schematically, this is schematic, but I've schematically plotted the vacuum energy of the different locally stable vacua from analyzing this potential. And so the main feature is, at small m, small SUSY-breaking parameter, there is a vacuum with the monopole field Vev set to 0, and this vacuum at some point at larger m becomes unstable due to this tachyonic monopole mass, and the potential wants to roll onto some branch where the monopole Vev is turned on. And so in this small m vacuum, the theory is in a Coulomb phase, or this vacuum is a Coulomb phase. And then at larger m, at some point, I can turn on this H non-zero branch becomes accessible to me. So H gets a Vev, and on this branch, the magnetic photon gets a mass, and this is interpreted as confinement. So there's going to be some crossover point, I'm calling it M star here, where I move via a first order phase transition from this small m phase to this large m phase with confinement. It's first order because even though the vacuum energies are degenerate here, these branches are disconnected in field space. And so in this large M vacuum, since H, this monopole scalar, gets a Vev, and it's an SU2R doublet, it breaks the chiral SU2R to U1R, reproducing this expected chiral symmetry breaking pattern of the CP1 phase. And then the two Goldstone bosons of this chiral symmetry breaking describe a CP1. And this was analysis at the monopole point, but there's a second CP1 at the dion point. So that worked out very nicely in the SU2 case. And an immediate generalization of what lesson we learned there for larger N is that we should look, if we're hoping to reproduce some CP1 phase, we should look at singular points of the moduli space, because these monopole fields have the right quantum numbers to break the chiral SU2 symmetry and to Higgs the U1 gauge factors, leading to possibly a confining phase. So, however, for N greater than 2, there are many additional singular points on the moduli space. So why should I look at the so why should I look at these multi-monopole points in particular? So some comments. The first is that these multi-monopole points, these are the unique points with n-1 massless mutually local scalars that can then Higgs the whole gauge symmetry. So if I want to reach some phase with confinement, I need to Higgs the whole U1 to the n-1 gauge symmetry. The second comment is that these the multi-monopole points lie on a special slice of moduli space for which charge conjugation and time reversal are preserved. So they already have at the Lagrangian level, they already have these features, these discrete symmetries that we know adjoint QCD has. And then the third comment is proximity to the n=1 vacua. So what I mean by this is that we know the CP1 phase, the proposed CP1 phase of adjoint QCD, is close to the n=1 vacua, in the sense that when I add the small fermion mass deformations, I match on to the n=1 vacua from the CP1 phase. And separately, I know that the multi-monopole points in Seiberg-Witten theory, these exactly become the n=1 vacua upon deformation by the n=1 preserving deformation.
I'm sorry, may I ask about this a little bit back to, n=2?
Yeah.
That when, this monopole condensation occurs and, you have a confinement, the feature of this confinement it's this, I don't know how called U1 confinement or whatever. It's not the one which we would like to have in QCD, because this kind of vertices, things which would appear would be not the one we would like to have for real QCD description. And in this sense, at least when we consider this range of small m, where it's not big one, in terms of superconductivity, the superconductivity of the first kind, the one where these strings are trying to attract each other, and so it's and it is not what you would like to have at your face at the end of the day. I mean, for the real QCD. So I'm not sure, maybe it would change for large m, right? But at least in the vicinity of small m, this kind of stuff which would show that it's not the confinement we are going after. I'm sorry that I'm interrupting you.
Yeah, no problem. So I'm not sure I understand what you mean by this isn't the confinement we're going after. I mean, this is like interpreted as confinement from the perspective.
No, it is confinement, but it's confinement which gives you a spectra which doesn't correspond to a spectra which we would like to have in QCD, because you can talk about this kind of strings, right? It is a standard picture. Our confinement, then you can find out, can verify that it is hadronic spectrum would be different from what the one. No, I mean, I am not trying to discuss all these details, but you can check that it's a different type of spectrum, and it is what bothers people, that it is this. And I am trying to put it in different language, that it is superconductivity of the first kind, not superconductivity of the second type. I mean, where like because of phase, yeah. And
okay, yeah. Yeah, thank you for the.
Yeah.
Go ahead. No, thank you for the comment. Yeah, maybe we can discuss. Maybe we can discuss later then.
Okay, I'm sorry.
Yeah, thank you. Okay, so yeah, thank you for the comment. I've motivated for you that we should look at these multi-monopole points, and for the rest of this talk, this is exactly what I'm going to do. So I'm going to take my starting point for analysis of the SUSY-breaking deformation, the effective theory of the n=2 theory near the multi-monopole point plus this deformation. And I'm going to work in the duality frame where the n-1 light states are monopoles. So now I just gave you lots of good reasons why this is a good idea. However, you should have in mind that even with these nice motivations, there are some qualitative puzzles that will need resolving for the n greater than 2 case. So the first basic puzzle is that, well, in some sense, there are n-1 copies of the SU2 case for SUN, by which I mean there are n-1 U1 groups, there are n-1 sets of the SU2 matter content. And so how is it that will I get a phase where all of the Higgs vevs, these monopole vevs, align to preserve the U1R symmetry? This seems like a very non-generic situation. Will that come out? Also, relatedly, how does a single CP1 come out rather than, say, n-1 copies of a CP1? So that's some first basic puzzle. The second is that, well, of course, for this SUN case, there's the possibility for many more phase transitions as a function of M. For SU2, I showed you this nice phase diagram as a function of M with a single first order phase transition to this confining phase. And so for general N, what is the pattern of phases and transitions? This will have a lot more structure. And then thirdly, I told you that this effective theory we're going to start at, it has these nice discrete symmetries that we want to be preserved. However, of course, these could be spontaneously broken by vacua. So are they spontaneously broken? Like what leads to them being broken or preserved, like we might want for a CP1 phase? And so for the rest of this talk, I'd like to resolve these puzzles and explain how this comes out. So what I'll do is first let me just introduce in a little bit more detail this effective Lagrangian that we're going to be working with near the multi-monopole points. So here I'm just going to give some more details about the scalar sector of this theory. The fermions and the gauge fields are completely fixed. Their couplings are completely fixed by n=2 supersymmetry. So here I've written the kinetic terms for these scalars. These are the abelian vector multiplet scalars. These are the hypermultiplet scalars, these monopole fields. And one thing I'll point out is here, I'm using this supersymmetry friendly normalization of having the effective matrix of couplings here in the kinetic term for the abelian vector multiplet scalars. And so this T matrix, this TMN, this is the effective matrix of couplings in the supersymmetric abelian Higgs model describing the effective theory near these multi-monopole points. And the eigenvalues of this matrix are 1 over the couplings. And so, and I'll give you some more details and comments on this matrix on the next slide. So the scalar potential then in this model is is given here. So first I've written the supersymmetric part of the scalar potential. It's quartic, for example, these are like the D terms that are quartic in the H's. And again, I'm using these little m and n indices to index the U1 to the n-1 gauge groups. And any equations I write on slides will typically have twiddles, and twiddles just mean I'm dropping factors of 2 and pi and so on to make the slides nicer. And then I add to the supersymmetric potential the SUSY-breaking deformation. So to determine what this deformation flows to near the multi-monopole points, I must match the IR stress tensor to the stress tensor on the Coulomb branch upon integrating out the light monopoles. So I already had some comments on this earlier in the SU2 case where I wrote the similar formula for the SU2 case, and I'll just point out the features again which hold for general N. So the SUSY-breaking deformation gives this tachyonic mass to the monopole scalars. It gives a positive mass to the abelian vector multiplet scalars. And I get the same sort of tadpole term from matching to the Coulomb branch expression upon integrating out the light monopoles. The last comment is that, as promised, this effective Lagrangian satisfies the discrete symmetries I said it should, in particular charge conjugation and time reversal. And so, for example, the way that charge conjugation acts on these IR fields is by permuting these little m U1 indices to n minus m of themselves on the scalars here. And so in particular, you can stare at these formulas and see that that charge conjugation indeed is preserved, since in fact this T matrix of effective couplings also has the same symmetry property. And then also this sign that appears in the tadpole has the same symmetry property of little m to big N minus little m. So I'd like to highlight the role of this matrix of effective couplings in the abelian Higgs model, this T matrix. So this is a purely supersymmetric object, and maybe somewhat surprisingly hadn't been computed before at the order to which we needed it. So we computed it. We computed in particular these matching contributions by doing a strong coupling expansion of the period integrals in Seiberg-Witten theory near these multi-monopole points. And so some comments on these terms. The important comment is, so, okay, these matching contributions, they have this interesting structure. Here I've written what the result of our computation is in terms of, you can give it in terms of sines and cosines. But a main feature to point out is that there are these off-diagonal matching contributions. And in particular, these couple the U1, the n-1 U1 gauge group factors in an interesting way, and this will be important. This fact is important for resolving some of the puzzles I posed to you earlier. Some more comments on these couplings. So this T matrix depends on the renormalization scale mu at which I define my theory. So in a full quantum mechanical treatment, this RG scale mu, so these couplings run logarithmically, defines the cutoff for my theory. But for my purposes of a semi-classical analysis, we can treat it as part of the definition of the model. Now, with that being said, these couplings, this matrix of couplings must be positive definite. And so this does set a scale below which the effective description of the effective theory near the multi-monopole points as this abelian Higgs model is valid. And so you can we explicitly computed, given these formulas I wrote up there, that this positive definite scale scales like lambda over n squared. And in fact, this also coincides with the scale of the masses of the lightest W bosons in the theory. So these are the lightest massive BPS states at the multi-monopole point. And so this sets some cutoff for my theory. So to make a comment here, that this cutoff scale, lambda over n squared, it looks small, and it is small. And the fact that this cutoff goes to 0 at large n is related to the fact that the large n limit of this theory is somewhat subtle. This was discussed by Douglas and Schenker. Now, for my purposes, we have gotten we've really gotten no mileage out of a large n limit, partly related to this. So everything I tell you are results that are finite in n. However, what I'm doing here, as I'm doing here, giving you some like n scaling, I'll do this at other places for other quantities because sometimes just to get some intuition, to have some quantities scale with n, or to simplify some complicated expressions. So that's some aside on the n dependence of things. So some important comments before I tell you about the resulting phase structure of this model. So this model only reliably describes the effect of deforming Seiberg-Witten theory in some very strict regime of parameter space. So first of all, there's this cutoff of lambda over n squared I just told you about for the validity of the effective description. So this also defines some cutoff on my phase space. And sorry, just to emphasize if it wasn't clear, so the monopole point in this description is when all of these phi scalars are at 0 exactly. So so that's some cutoff for the validity of the supersymmetric description. Of course, as I've already told you, to reliably analyze, I need this SUSY-breaking scale m to be small compared to the strong coupling scale, and this is because I'm dropping higher order terms in m over lambda in this SUSY-breaking deformation that I wrote down for you. I'm keeping the m squared part of it, and so you should ask what actually happens when I analyze this model I've described for you in this regime of parameter space. And the answer is absolutely nothing, that you get no valid semi-classical solutions. So we will allow ourselves to explore beyond these strict limits and hope that the effective description will capture the phase structure in a qualitative way. And so I think—
Emily, may I ask
yes.
something? Emily,
Yes.
this is Eric. So
Hi.
I have a question. In the SU2 case, the analysis would valid semi-classically, correct?
No, so in the SU2 case,
No.
the matching contribution was large, and so the coupling was strictly speaking large. And
I see.
And so yeah.
So it's similar. Okay, thank you.
Very similar, very similar.
But I also have a question about this piece that, yeah, maybe I got it wrong, but when you are saying that at large n, your W boson mass becomes 1 over n squared, right? I mean, lambda divide small at large m, then I would be thinking that this mass of W boson itself serves as a cutoff. So
that's
when
right.
Right, but then you're saying m much smaller than lambda, then it's a different cutoff, because I'm trying to differentiate between lambda divided by n squared, or
That's right. That's right. These are two different cutoffs. These are two logically different cutoffs, and they both should be true.
Right, but I would say that effective description without W boson certainly doesn't work in the range of mass which is larger than lambda divided by n squared. Because then your W boson are also light, right? It's how you will forget them.
But what I mean is, if I need to evaluate, like, so the W boson mass is some cutoff, and I need to evaluate my theory below the scale of that cutoff, so that it's okay that I'm forgetting about them.
Yeah, right. So it means that you are applying your theory, effective theory, below mass of W's, right?
That's right. That's right. Yes, that's correct.
But then I would say that m also should be smaller than this. Large m.
Oh, sure.
You see, and when you are saying that m is much smaller than lambda, no, of course it's there, but I'm trying to say that it is more strong.
I see your point. Yes. So this is coarse. This is some coarse statement, and you could refine this statement by the sort of thing you're talking about. That's true.
Okay. Thank you.
Yes. Thanks. And so, okay, so I'm telling you there are no solutions within the strict regime of validity, but I'm going to allow myself to explore beyond this. And I think this is a good case of maybe the ends justify the means to a certain extent. If we got nonsense, then okay, we would get nonsense. But the fact that we get some nice consistent picture, I think maybe justifies allowing ourselves to probe beyond these limits. Okay, so with that being said, let me describe for you the results of studying this phase structure. So first of all, at small m, just like was the case for SU2, I get a minimum, which is a Coulomb phase vacuum with all the monopole fields set to 0. So I can solve exactly in n. I'll give you some formulas just to see how things scale with n. So basically at small m, the monopole vevs sit at the origin. My potential looks like this first line of this big potential that I've written in full here for the SUN case. And so schematically, what's happening is this tadpole is setting the scale of the vev of the vector multiplet scalars. And so that's why I get this sign here. And so in particular, immediately you can see my vector multiplet scalars go like sine pi m over n and times lambda. And even the smallest of these, which have little m order 1 compared to n, scale larger than this cutoff. So just to point out, everything I'm going to tell you is larger than this cutoff. Okay. The second comment is that much like in SU2, the small m phase vacuum is only stable below some bound. And this bound, it goes like, I'm going to call it MCB for the Coulomb branch, because this is a Coulomb phase vacuum. And this bound goes like lambda over n. Okay, again, bigger than the cutoff. But then beyond this bound, so at larger m, so vacua with some h's turned on will take over. I'll want to roll into some vacuum with some of these h vevs turned on. And so that's what I'll describe next. One other comment is I can compute the vacuum energy of this vacuum, and it scales like minus n squared, and I just minus m squared lambda squared n squared, and I just want to comment that this matches the scaling of the vacuum energy if I compute it at the origin of moduli space, so just on the Coulomb branch at the origin. And so the lesson of studying this small m vacuum that I want to emphasize is that it qualitatively captures the features of the Coulomb phase of the supersymmetric theory at small m. So it makes sense that we're getting these features. So now I'd like to tell you about general properties of the phases that hold for larger m. So first, let's consider the fate of CT in vacua. So here I've just written this full SUN potential that we're analyzing. So the first feature, which comes out of analyzing this potential, is that all saddle points of this potential preserve CT. You can check this. You can just check that all saddle points of this potential have 5 vevs, vector multiplet scalar vevs, that are purely imaginary. So here I'm writing them as, I can write them as I times some real number. So I'll put x's on later slides that are real. And the point is that when the 5 vevs are purely imaginary, they preserve CT. CT acts like this on vevs. And so this is a non-trivial statement, and it holds in particular for all n greater than or equal to 2. For n equals 2, there's no charge conjugation, and it would just be t, but the same argument holds. So this is really interesting. We know that CT has to be preserved in whatever phase is realized by adjoint QCD due to the Vafa-Witten theorem. However, the Vafa-Witten theorem does not apply here to the supersymmetric theory. Here, I get this feature that CT will be preserved in vacua simply from the structure of this potential, and in particular, it follows from the form of the tadpole. So this tadpole is setting the fact that my 5 vevs are purely imaginary. And this tadpole came from matching to Seiberg-Witten theory near the multi-monopole point. So this is some input from Seiberg-Witten theory. Feature 2 is what happens to the chiral SU2R symmetry. So the feature, which is new for n greater than 2, is that we need to consider the alignment of multiple H vevs in SU2R space. So in this little I index. So, so what you can check is if I write all the terms in the potential that depend on the relative alignment of H vevs in SU2R space, and I rewrite them in some nice SO3 variables, then I get this expression, which is it's just a spin chain, and the behavior plus things that don't depend on the relative alignment of these vevs, and the behavior of the spin chain is entirely dictated by the sign of these of the coefficients, and these coefficients are elements of the inverse matrix of effective couplings. And a non-trivial feature is that these are all negative as long as our cutoff, we're taking our cutoff to not be too large. So because of this, the potential looks like a ferromagnetic spin chain, and all of the H's will align for a minimum of the potential. And so we get the result that a global minimum of this potential with some of the H's non-zero will preserve a U1R. So again, this is a non-trivial statement that was not required by Vafa-Witten. We know Vafa-Witten should apply at very large M to whatever phase is realized by adjoint QCD. But this is a fact of any phase of this potential that's realized at intermediate M, and it ensures consistency with Vafa-Witten at the end of the day. And so kind of the lesson is that this chiral symmetry breaking pattern of SU2R to U1R is actually a robust feature of this effective model that I'm presenting to you. And it's due to the non-trivial off-diagonal structure of this T matrix. Third, you can ask what happens to charge conjugation. So I told you CT is preserved. What about C separately? And so the feature which is new for n greater than 2 is that, well, I have charge conjugation and it acts how I told you it acts on the scalar vevs. Here, because of the last slide, the alignment of the H vevs, I can drop this I index, and now I can write everything in terms of real variables. So that's just an aside. So, okay, what happens to charge conjugation? Whether or not this is spontaneously broken by vacua has to be checked for the vacuum solutions. So this doesn't follow by some general feature, it has to be checked. And the result is that there are metastable vacua that break C. However, the globally stable vacua preserve C. And so this is a result of the dynamics. So I'd like to explain this with an example. I'd like to show you an example, and so I'll do a test case of SU3. So in SU3, there's exactly one C conjugate pair of variables. I have H1 and H2, and similarly phi1 and phi2. And so there are 3 possible branches. I could have both of the Higgs vevs sitting at 0. This is this small m branch that I've already discussed. I can have one of these H's non-zero. This would be some branch that breaks charge conjugation. And then I could have both of them non-zero. And so let's focus on this case for the moment with both of them non-zero. So the result of a stability analysis, by which I mean checking for positive definite Hessian for these vacua, is that vacua with H1 and H2 both non-zero, these preserve charge conjugation. So for SU3, this means H1 equals H2 equals, I can call it H, and X1 equals X2 equals X similarly. So here I'm using this real variable X for the vector multiplet scalars. So then the extremization conditions simplify. I've written them here, and I want to point out 2 features that follow from solving these equations. So the first feature, so the first feature follows by checking for for what the H vev does. So here I'm considering a vacuum in which H1 equals H2 equals H is turned on, and H squared goes like M squared minus X squared. Okay, so this defines some region of X that I've shaded here in really light green, for which h squared is positive. So I get a possible solution to this equation. Then I can do a stability analysis of the possible vacua, and I can check that actually the region of local stability of solutions in X is strictly smaller than this region that reaches out to h equals 0. So the fact that the locally stable solutions are necessarily disconnected from the solution that connects onto h equals 0 means that there's going to be a first order phase transition between this phase and any phase with one or both h's equals 0. So the second comment is, okay, so let's plug in this h squared solution into this equation for X and get some effective equation that determines what my xvev is going to be. And so when I plug this in, I get some cubic equation in the X, the vector multiplet vev, and that's what I've plotted on this plot. So when this curve for X crosses the horizontal axis here, that's when I get a solution to these equations. And so whether this curve can cross the x-axis depends on m, and in particular, larger m is the SUSY-breaking scale, move this curve up, and for m large enough, this curve moves up so that I get a solution within this allowed regime of parameter space, this blue curve. So therefore, there's going to be some minimum m for which this branch with the h's turned on can turn on, and so that's this minimum. I'm calling it mhb for m quote unquote Higgs branch. So that's how some of these features come out. So what's the result? So here I've plotted schematically that resulting SU3 phase diagram. So again, I'm schematically plotting the vacuum energy as a function of m. We've discussed this small m phase, which is has all the h's equals 0 and is in a Coulomb phase. Now, like I just told you, at some m equals this mhb, locally, I'll get a stable solution with h1 equals h2, both turned on, and that'll be locally stable. And actually, I'll also get, I didn't describe this solution for you, but a result is I'll also get a metastable solution with only one of the h's turned on, which breaks C. So then I get a phase diagram that looks like this, where I'm plotting all the possible locally stable solutions. And so this phase diagram, aside from this metastable solution, looks very much like the SU2 phase diagram I showed you earlier. And indeed, it has the same qualitative features of this first order phase transition. And that actually follows because both satisfy a similar cubic equation that thing I was plotting on the previous slide. So then at large m, I transition into a vacuum with both of these h's turned on. Charge conjugation and time reversal are separately conserved. The magnetic U1 squared symmetry is completely Higgsed by the two h-vevs. And this is then a confining phase of my theory. Now, in this phase, another result is that the only massless degrees of freedom are the two Goldstone bosons that parameterize the CP1. So the comment is, and so this result also will hold for larger n, not just SU3. So the comment is that if this T matrix were diagonal and these U1s were not decoupled, I would have had more massless scalars, more than just these two Goldstone bosons. However, because all these U1s are coupled together, I get all these other modes are lifted, and I get exactly the two Goldstone bosons parameterizing the CP1. So that's a nice result. So okay, so what happens for general n? So for general n greater than 3, this n equals 3 case I just showed you, a new feature is that I have multiple C symmetric pairs. So H1 and Hn-1, H2 and Hn-2. And so relative to SU3, I have the possibility for more phase transitions as I dial up M. And so the result that we find is that we find a sequence of phase transitions as C-symmetric pairs of HVEVs turn on one at a time. So the first transition to an H1 equals Hn minus 1 vacuum, this first transition really satisfies, like really the SU3 intuition completely holds. Basically X1, Xn minus 1 satisfy a similar cubic. And so I'm going to plot for you, for example, this first phase transition here. This is an example where I'm doing numerics for SU4. So let me explain. So this is the not schematic version of this schematic plot I've been showing you, the vacuum energy as a function of M. And here I'm just zooming in, doing some numerics for the SU4 case on this first phase transition region. And it has this feature I described to you of a phase transition between this no H Coulomb phase vacuum and this first transition to a, in this case for SU4, it would be H1 equals H3 vacuum, and then there's this metastable C-breaking vacuum that hangs around. Now for SU4, I have a second opportunity for a transition because I have, in addition to the C conjugate pair H1 and H3, I have a self conjugate H2. And so if I zoom out, so this is a picture where I'm just zooming out of this picture I just showed you of this first transition. This box is that picture I just showed you on the previous slide. Then I'll find at a larger value of M, I transition into the phase with all H's turned on. And then the general result, which I can see by expanding for general N for large M, is that I will transition to some, at large M, to some all H's turned on vacuum, which is C and T symmetric, and which is the global minimum of the potential. And again, this is an exact statement in N. So I'll just, I'll end by giving you, before I end, I'll just give you some more features of this large M phase that we find. So the first feature is something I haven't pointed out yet, which is the fact that these HVEVs, they induce a UV Gaugino condensate. So supersymmetry relates the Gaugino condensate in this case to a descendant of the U2, this trace phi squared Coulomb branch operator. And so I can expand this expression near the multi-monopole point, and I get some expression that depends on these HVEVs. And so I can compute using what I know about this T matrix and about, like, I can solve for these HVEVs analytically at large M. And what I get is I get a Gaugino condensate that scales like N. And this is exactly the expected scaling of a Gaugino condensate in a theory with adjoints. And again, this came just from this SUSY-breaking N equals 2 analysis. So that's an interesting and non-trivial cross-check that we're on the right path to describing adjoints. Now this phase of the Gaugino condensate I wrote here, this is the phase at one of the multi-monopole points. Remember, I told you there are N multi-monopole points, and so there will be N phases of the Gaugino condensate related by this Zn. So we get one CP1 here, and then we'll get N CP1s, N copies of the CP1 at the other points. Then the second comment is I can compute the vacuum energy in this large M phase with all the H's turned on. And again, by non-trivial properties of computing how these effective couplings depend on N, I get a result that looks like minus N squared. And in particular, again, this check mark is because this is exactly the N scaling I expect for the vacuum energy in a theory with adjoints. So another non-trivial check. And this non-trivial check is due to the detailed structure of this T matrix. This was crucial to getting out these large N scalings. So I'll end with some brief summary of the properties of these phases that I've been describing to you. So I described for you a series of phase transitions, and there were intermediate phases with some HVEFs turned on, and I told you the global minimum at large M is this phase with all the HVEFs turned on. And here I'm just summarizing the properties of this phase, and it features exactly these CP1 properties I was expecting. It features confinement. It features this SU2R to U1R chiral symmetry breaking pattern, which, like I told you, came from the structure of this T matrix. CT are preserved, which came from basically the structure of the tadpole from matching to Seiberg-Witten theory, but C is also separately preserved in this vacuum, and that's a feature of the dynamics. There are exactly 2 massless scalars, and I told you this is because the off-diagonal terms in T couple all these U1s, so I get exactly 1 CP1 coming out, and everything else is massive. So again, I match exactly the expected properties of the CP1 phase of adjoint QCD. And so I'll just finish with a brief summary. So I set out to interpolate between Seiberg-Witten theory and adjoint QCD by adding a soft supersymmetry-breaking mass to the vector multiplet scalars. And I motivated that we should study an effective Lagrangian that derives from Seiberg-Witten theory with the SUSY-breaking deformation turned on, expanded near the multi-monopole points of the n equals 2 moduli space. And then I described for you some results that using this semi-classical Lagrangian, I can get a sequence of first-order phase transitions, or I get a sequence of first-order phase transitions that interpolate between the small m Coulomb phase of the supersymmetric theory and a phase with all the nice properties of the CP1 that I kind of listed out for you at large M. And in this large M phase, all the monopole fields condense, and this leads to confinement and chiral symmetry breaking. So yes, thank you for your attention. I'll stop here.
Thank you, Emily, for the wonderful talk. Let's see, we have time for questions.
May I ask a question?
Yes.
Emily, I have a question about the intermediate phases. If you show your next to last slide, you said that there is no confinement in them. And I'm a little confused. Say for SU3, you had a phase where one monopole condensed and the other didn't, right?
So for SU3, I had a phase where both monopoles condensed. So okay, I had a metastable phase for which one monopole condensed, but then the stable phase, like the globally stable phase, had only both of them condensing.
Yeah, my question is about that phase. So does this, so I would think that there is confinement in that phase, no?
Well, so you can check that, I didn't describe this, but you can check that the one form symmetry is broken in that phase. So
I see, but when the monopole, so how do you see that when you have a condensed monopole, you expect to have a flux tube. You're saying it's unstable. So I would think that some component of a fundamental would be confined. Maybe the flux tube is unstable, but I'm just curious how that works. How did you check that the center is broken? Sorry.
So you can check that so you can check that the one form symmetry, it's embedded in the diagonal U1 of the U1 to the n-1 one-form magnetic accidental one-form magnetic symmetries of the abelian Higgs model, and as long as not every Higgs field is turned on, there's some charges that are going to break, that are just going to completely break that diagonal U1.
I see. Okay.
Thank you. Any questions?
Ken, I raise a hand, but you can I ask? May I ask?
Sorry, Arkady, I didn't notice. Yes, please. Ask.
Okay, but probably No, Emily, I apologize because my recollections of what I was kind of thinking about this stuff, it's like 20 years ago. so it's, but I'm trying just to add a little bit. Remember when I asked a question about this spectrum, it's related partly to what Eric was asking about. You have this flux tubes. When you have this monopole confinement, and then when we did try to follow this up with Alexei Jung, the issue was that, say, in SU2 case, n equal 2, then this flux could be not only n equal 1, but it could be larger fluxes as well. Okay, and when I said that it is first kind of superconductor, it means that higher fluxes are stable. So you have things not only kind of with minimal flux, but say twice flux and so on. Okay, and this of course then it would show up in this hadronic spectrum when you have, say, mesons which are coupled by strings, right? And in the case of larger NC, larger number of colors, it was, I believe, Douglas and Schenker who noticed that because you have a different kind of these strings, right? Then you can find out when you consider this fundamental, Q-bar-Q pairs, mesonic pairs, then number of your mesons would be growing with NC as well, like NC plus 1 divided by 2. Integer part of it. Okay, and it's related to this phase diagram which you discussed, where the center, what center is realized, center of the group, or okay. So I'm just trying to make it more clear what I was asking about.
Yeah, thank you. So just a small comment is that so for us, when we study the strings, we have to study them with this mass deformation here, not like this Douglas Schenker deformation was the n equals 1 preserving deformation. But yeah, thank you. I see what your question.
Okay, thank you.
Are there any other questions or comments? Okay, if not, let's thank Emily again for the great talk, and maybe we can turn off the recording if people want to ask other questions informally. We can continue. Thanks again, Emily.
Thank you.